So, you've just been introduced to derivatives, and suddenly you're seeing weird symbols like f prime or dy dx. What do they mean? And why are there so many ways to notate the derivative? Recall that a derivative is just a fancy word for a rate of change. It tells you how fast something is changing at any point, like how fast your car is going on the highway at a specific moment, or how fast water is draining out of a container at a certain time. Just like anything else in math, derivatives come with their own special notations. But multiple notations? Why is that necessary? Well, let's think about division. We can write division in multiple ways, like a over b, a divided by b, or even a times b to the power of -1. They all mean the same thing, but each is useful in different situations. Derivative notation works the same way. Each notation highlights something slightly different depending on the context. One of the most descriptive notations is the Leibniz notation. It means the derivative of y with respect to x. In other words, if y depends on x, this shows how a small change in x affects y. Remember when we defined derivatives, we were considering the change in y over the change in x for 2 points. This is the average rate of change, and the changes in x and y are a fixed, finite value. But to find the derivative, the 2 points move infinitely close to each other, and the average rate of change becomes the instantaneous rate of change. Remember, we define the derivative using limits. It's the limit as the change in x approaches 0 of the ratio the change in y over the change in x. That becomes dy over dx, the rate of change of y with respect to x using infinitesimally small changes. Just like the delta sign is a finite change, the d is an infinitesimal change. So dux is a tiny change in x, and dy is a matching change in y. For example, if we had this graph, y equals x squared, when x has a very small increment from 0 to 0.04, y goes from 0 to 0.0016. Thus, the secant line at this point will have a slope of the change in y over the change in x, or 0.04. Now, imagine this change in x getting smaller and smaller. This is represented by dy over dx, which is the derivative, the slope of the tangent line. In this example, we know that the derivative of this function, x squared, when x is 0, is 0, because the tangent line at 0 has a slope of 0. Now, the x and y are just variables in function names, so we can change this. Instead of y, let's say f of u equals u squared. If we wanted to take the derivative of f with respect to its input, u, we can notate this as df over du. Now, sometimes you will also see the Leibniz notation used as an operator. Here, we're applying the derivative operator to the function f of x. Really, this is the same as df dx, just different ways to notate the same concept. Okay, so that's a little bit about the Leibniz notation. Another common notation is the Lagrange notation, which is a bit cleaner. It looks like this. All this means is the derivative of the function f at point x. It's short, neat, and perfect when you're only dealing with one function. For example, if f of x equals x to the power of 3, and we know the derivative of f of x with respect to x is 3x squared, then we can write f prime of x equals 3x squared. Short, simple, and efficient. And the two notations still mean the same thing, the derivative of f of x. The Leibniz and Lagrange notations are two very common notations for derivatives. A couple other popular shorthands you might see in physics or mechanics courses are Newton and Euler notations. All of these mean the same thing, take the derivative of y with respect to x. So, just like any other mathematical concept, there are different ways you can notate the derivative. And remember that just like with division, the different formats exist to show different perspectives. For example, a divided by b is simple and clean, great for basic arithmetic. A over b gives a clear structure, especially in algebra. And this method of writing division is super helpful for long division. Same idea for derivatives. F prime is short and clean when dealing with single variable functions. dy over dx makes it obvious what variables you're differentiating. This notation treats the derivative like an operator and is super useful in advanced math and physics. Each one is valid and each is useful depending on what you're doing. Alright, now let's touch on higher derivatives. To notate second derivatives or higher, the notations change slightly. In Leibniz notation, the order of the derivative is written as a superscript on both the d in the numerator and the x in the denominator. If the placement seems kind of random, think of it like applying the d over dx operator over and over again, kind of like raising it to a power. And for Lagrange notation, we use apostrophes for the first few. F prime, F double prime, F triple prime, and then starting at the fourth derivative, we switch to the actual order of the derivative, like 4, 5, and so on. Higher derivatives for Euler and Newton notations are pretty straightforward. For Newton, just add more dots, and for Euler, just show the order as a superscripted number. All these notations point to the same exact concept of derivatives. And now, you know what all of these different notations mean. Leibniz, Lagrange, Newton, or Euler, all of them stand for derivatives. These aren't just weird math shorthand. They're different ways to communicate the same powerful idea of derivatives. Each notation tells the same story, just in its own unique way. And depending on the setting, one form might be cleaner, more expressive, or just more convenient than the others. And that's all about derivative notation. If you learned something in this video or enjoyed this, don't forget to like, subscribe, and share it with a friend. Keep working hard and keep learning. Thank you for watching.